Hello everyone, my name is Karan Chauhan and my roll number is IT2K2325. Today in this video we will be discussing the end semester solutions of data science. So now let's get started. So here's our question number 1, part A. Distinguish between hypothesis driven and data driven paradigms when data science. Provide an example of each. So here's our table. So let's get started. Aspect starting point hypothesis driven begins from a predefined theory assumption or research question, while data driven begins from available data without a strong prior theory. The main goal is to test whether a specific hypothesis is true or false in hypothesis driven, while in data driven it discovers patterns, correlations or structures in data. Hypothesis driven approaches detectives moves from theory to data collection and testing, while in data driven it is inductive moves from data exploration to forming new hypotheses. In data collection, data is collected in controlled way to answer a precise question in hypothesis driven, while in the data driven, it uses large, often existing data sets. Collection may be broad and open. Typical techniques in hypothesis driven are statistical tests, controlled experiments, A/B testing, while in data driven, data mining, machine learning, clustering, predictive modeling. Role of domain knowledge in hypothesis driven is very strong. Domain expert defines hypotheses and variables, while in data driven it is important but sometimes secondary to algorithmic discoveries. As for the flexibility in hypothesis driven, it is less flexible, limited to hypothesis defined beforehand, while in the data driven it is more flexible, can reveal unexpected patterns and new questions. So our next question is differentiate between structured, unstructured, quantitative, categorical data with suitable real world examples. So okay, here's a difference between structured and unstructured data. The aspects are organization. In structured data, it is highly organized into predefined rows, columns, and data types, while in unstructured, no fixed schema information is free from loosely organized. While talking about storage format in structured data, relational databases, spreadsheets, CSV tables, while in unstructured, it is text documents, images, audios, videos, social media posts, etc. Ease of querying, easy to query using SQL and similar query languages, while in unstructured it is difficult to query directly, often need pre-processing and algorithms. Typical analysis in structured data. Descriptive statistics, dashboards, traditional BL, ML models, while in unstructured data it is text mining, NPL, image processing, speech recognition, deep learning. Examples of structured data are bank transaction tables, student marks tables, sensor logs. While in unstructured data, these are emails, customer reviews, photos from CCTV, recorded phone calls. Explanation with examples. Structured data follows a strict schema, such as table with columns, customer ID, age, income, city, where each row is represent a single customer and each column has a predefined data type. Bank databases or hospital patient record are good examples. In contrast, unstructured data does not fit into neatly into tables. Examples including a folder of a PDF report, a collection of tweets about a product, or surveillance video where the useful information is hidden in raw text, audio, images, or etc. must be extracted using specialized algorithms. Next is the difference between quantitative and categorical data. So let's now look into it. The aspects are nature of values. In quantitative data, numerical values that represent counts or measurement. In categorical data, non-numerical labels or categories describing qualities. Main purpose is used to arithmetic operations like addition, mean, variance, while in categorical data, it is used for grouping, classification, and frequency counts. The subtypes of quantitative data are discrete counts, continuous measurements, while in categorical data are nominal, no order, ordinal, ordered categories. Allowed operations can compute some averages, standard deviation, correlations, while in categorical data it can compute mode, proportions, cross tables, numeric codes, and have no arithmetic meaning. Okay, so the examples of quantitative data are height in centimeters, weight in kilograms, monthly income, exam scores. While in categorical data, examples are gender, blood group, product category, customer satisfaction level, low, medium, high. It can depend on the customer satisfaction. Okay, so the explanation with example is quantitative data consists of numeric values where mathematical operations make sense, such as the number of items sold per day, the temperature recorded by a sensor, or the speed of a vehicle. These measurements allow calculations like average growth rates and correlations. Growth rates and correlations. Categorical data represent qualitative attributes or group labels such as male, female, other, gold, silver, bronze, membership levels, or yes, no response in a survey. Numbers may be used for codes, for example, one for male, two for female, but these codes are for identifiers and should not be treated as a real numeric quantities. So now let's look at question number two. Question number two, part A. Write an algorithm that uses Bayes' theorem for decision making. Part B. Write any suitable algorithm for association rule mining that can print all association rules. Okay, so now let's start. The goal is to decide the most probable class CK for an instance X using Bayes' theorem. So now let's start. The algorithm is identify all possible classes C1, C2, C3 up to CK and the relevant attributes, features of the instance X. Second, from training data, estimate the prior probability of each class P of Ci and the conditional probability of each attribute value given in a class P xi xj slash xi ci. Okay, and the third step is for the new instance x is equals to x1, comma x2, comma x3 up to xn. Compute the positive probability for every class using this formula that is given of the naive Bayes theorem. The proportionality means that the denominator px is the same for all classes, so it can be ignored for comparison. Step number 4 is to normalize the positives if required so that the probabilities sum to 1 across all classes. One sum to 1 across all the classes. The fifth step is to select the decision class label with maximum positile probabilities mapped decision. Decision is equals to argument maximum of p of c or ci slash x ci. The output of the chosen class of the instance X and needed its probability as confidence. This algorithm is commonly used in classification problems such as email spam detection or medical diagnosis. So now on to the question number 2, part B. Algorithm for association rule mining that prints all the association rules. So now let's get started. You can write an appropriate algorithm steps following by the rule generation from the frequent item sets. First one, appropriate to find the frequent item sets. First, input the transaction database D. Minimum support threshold. Second, generate the set of candidate 1 themselves C1 by listening all the individual items in the dataset. Third, scan the database to count the support of each candidate in C1. Keep only those who support uh, as support keep their support as maximum or equal to the minimum of support to form the frequent 1 items of L1. For the step 4, put k is equals to 2, comma 3, etc. Generate candidate k itself then ck by self joining lk minus 1 join step and removing those who any k minus 1 subset in a frequent prune step. Okay, scan the database to count the support of each candidate in ck from lk by keeping candidate with support that is greater than or equal to the minimum support. Stop when lk becomes empty. So the part 2 consists of generating and printing all the association rules. The first step is input all the frequent items L and minimum confidence. Second, for each frequent item set f in L with f is greater than or equal to 2, generate all non-empty proper subsets of subsets A of f. Second, for each subset A, let B is equals to f slash A. Compute confidence of A to B as confidence of A to B support of f divided by support of A. If confidence is greater than or equal to minimum confidence, print the rule A goes to B along with the support and its confidence. 3. Third step. After processing all the frequent item sets, all high confidence association rules are printed. This procedure mines items co-occurrence patterns. For example, bread butter is equals to jam. And the reporters all valid association rule that satisfy the given support and confidence thresholds. Now, question number 3. Part A says, compute mean, median, mode, and standard deviation for a given small dataset. Explain when each measure is appropriate. Part B, what is the difference between error and artifacts in data cleaning? Explain any two imputation techniques. Okay, so now let's get started with the part A. Mean, median, mode, standard deviation, and when to use them. Okay, take a small data set of marks 40, 50, 60, and 90. First, mean, that is the average. Formula of n values x1, x2, x3 up to xn. Mean is equals to summation of I is equals to 1 xi divided by n. For dataset, mean is equals to 40 plus 50 plus 50 plus 60 plus 90. So that gives 290 divided by 5. That gives 58. So our mean is 58. when appropriate, best for symmetric numeric data without extreme outliers, used in many statistical procedures and for overall performances like average marks or average income. Second is the median, middle value. Arrange data in ascending order 40, 50, 50, 60, 90. For odd and median is the middle value. Here median is 50. When appropriate, prefer when data is skewed or contains outliers. Example, salaries in a company. Given a better central value when one or two extreme values would distort the mean. Third is the mode. Mode is the most frequent value occurring in our dataset. The value occurring with highest frequency. In the dataset 50 appears twice, others appears once, so the mode is 50. When appropriate, useful for categorical or discrete data such as the most common blood group, favorite product, or most frequent grade, etc. Fourth is the standard deviation, spread of the data. First compute mean, that is the mu, that is 58 that we have already computed earlier. To find the deviation from the mean, that is 40 minus 58, that gives minus 18. 50 minus 58, that is minus 8. 50 minus 58, that gives minus 8. 60 minus 58, that gives 2. 90 minus 50, that gives 32. Okay, now we have to square the deviations. As we have squared the deviation, we have got the values 324, 64, 64, 4, 1024. Now we have to calculate the variance, that is the population, that is 324 plus 64 plus 64 plus 4 plus 1024 whole divided by 5, that gives 1480 divided by 5, that gives 296. Now on to the standard deviation. Standard deviation is the square root of variance. So now the square root of 296 gives approximate value as 17.2. So when do we use standard deviation? When it is appropriate to use standard deviation. Standard deviation is appropriate to use when because it indicates how tightly data points cluster around the mean. Small value means low variability, used in risk analysis, quality control, and comparing consistency of performances. For example, two students with the same mean marks but different spread. Here's the difference between errors in data and artifacts in data. Here are the aspects. First, basic meaning. So what are errors in data? Errors are the incorrect values that do not represent reality, while artifacts are the unwanted patterns or distortions introduced by the collection or processing. What is the typical causes for errors? It is typing mistakes, wrong units, misrecorded measurements, etc. For artifacts, those are sensor malfunctions, system glitches, pre-processing bugs, etc. Examples of errors are age recorded as 250, which is not possible. Negative salary, which is also not possible. Date 32 13 200 2024, that is not possible because any month doesn't have 32 as a day. For the artifacts in data, sudden spikes in ECG signals, duplicated records after import. Effect on analysis leads to wrong statistics, wrong models, misleading conclusions in errors in data. While for artifacts, creates artificial trends or correlation that are not truly present. Treatment in cleaning. How do we treat errors that are present in our data? Correct or remove incorrect values after verification. For artifacts, we detect sources of artifacts and filter, smooth, or remove the artifact affected data. The two imputation techniques are mean, median mode, mean and median imputations are replace missing numerical values by the mean or median of the attribute computed for non-missing records. Mean is suitable for roughly symmetric data. Median is better when data is skewed or has outliers. Simple to implement and quick for small medium datasets, but it can reduce natural variations because many records share the same imputed values. K nearest neighbors, K in an imputation. For a record with missing values, find K most similar records based on the other attributes, such as using data distance measure. Second is the for a numerical attribute, impute the missing value as the average of that attribute in the K neighbor. For a category, use the most frequent category among the neighbors. Okay, so now the third point is this method preserves local structure of data and often gives more realistic values than simple mean. But it is computationally more expensive and sensitive to the choice of distance metrics and K. Now on to our question number 4. We have part A as explain any 4 common feature engineering techniques for continuous or categorical data. Part B says that what is sampling from a distribution? Describe inverse transform sampling on Monte Carlo sampling with an example. So now let's get started. First part A. Scaling and normalization continuous. Rescale numeric features so that they are on similar range. Example, standardization, subtract mean, divide by standard deviation, or min-max scaling too. Help gradient-based model, linear regression, logistic regression, neural network, SVM, converge faster and prevent features with large units and dominating distance-based models like KNN or K-means. Second is the binning discretization, continuous to categorical. Converts a continuous variable into intervals or bins, such as turning age into groups 0 to 18, 90 to 35, 36 to 60, and 60 plus. Reduces noise and makes pattern easier to interpret, and is often used to in decision trees or risk scoring rules where ranges are more meaningful and exact numeric than exact numeric values. One hot encoding categorical. Transform the categorical feature with k possible values into k binary columns, including indicating presence 1 and absence 0 of one category. Fourth is the interaction and polynomial features. Continuous and categorical. Categorical. Creates new feature by combining existing one. For example, product of two variables area is equals to length into breadth. Or polynomial terms like x to the power 2 and x to the power 3. Captures non-linear relationships and interactions between variables that a simple linear model cannot express, improving predictive power when chosen carefully. Now on to the part B. Sampling from distribution and inverse transform, or Monte Carlo sampling, whatever you say that. Okay. So what is sampling from a distribution? Sampling from a distribution means generating random values such as their long run frequencies follow a specialized probability distribution, for example, normal exponential or Bernoulli's. In data science and statistics, this is used for simulation. Monte Carlo methods, bootstrapping, and creating synthetic databases when real data is limited or expensive to collect. Okay, so now we have inverse transform sampling with examples. Our goal is to generate sample from a continuous distribution with cumulative distribution function CDF f of x. So the steps are: first, generate a random number u from the standard uniform distribution on 0, 1. Second is to compute x is equals to f inverse u, where f inverse is the inverse CDF, also called quantile function. The third step is the value of x is a sample from the target distribution. Repeat steps 1 to 2 to get more samples. The examples are: suppose the target is an exponential distribution with a rate lambda. If CDS is f of x is equals to 1 minus e to the power minus lambda x, where x is greater than or equal to 0. To inverse at u is equals to f of x, which is equals to 1 minus e to the power minus lambda x, so that e to the power minus lambda x gives 1 minus u, that gives hence. Moving forward, we have our question number 5. The part A says that distinguish between parametric and non-parametric models and supervised versus non-supervised learning with examples. Okay. The part B says that define accuracy, precision, recall, F1 score, and illustrate their computation using a confusion matrix. So now let's get started. The first is the parametric versus non-parametric with example. Parametric models, non-parametric models, aspects that we are going to talk about. Okay. So number of parameters in a parametric model are fixed, independent, and data set size. And while in non-parametric models grows with data, complexity increases with more samples. Okay. Assumption on form. In parametric model, assume specific functional form, example linear. Make fewer assumptions about underlying function distribution in non-parametric models. Data required. Work well with smaller data sets, while non-parametric models usually need more data to generalize well. Training speed. Parametric models are typically faster, simpler, and optimization. Non-parametric models often slower, more memory intensive. The example of parametric models are linear regression, logistic regression, Naives Bayes. For non-parametric models, the examples are KNN decision trees, random forest, kernel SVM. Parametric models summarize the data using a dataset of parameters, for example, linear regression with a slope and no interchange. Easy to interpret, but sometimes too rigid when the true relationship is complex. Non-parametric models need to adapt their decision trees or KNN, which can model non-linear patterns, but risking overfitting is not regularized or pruned. Next is the supervised learning versus unsupervised learning. So now let's look at the aspects. The first aspect is availability of labels. The supervised learning uses labeled data. Each input has a known target output, while in unsupervised learning uses unlabeled data, only inputs, no target outputs. The goal of supervised learning is to learn mapping from inputs to outputs for prediction, while in unsupervised learning, it discovers hidden structures, groups, or patterns. Typical tasks for supervised learning are classification, regression. For unsupervised learning, it is clustering, dimensionally reduction, association mining. Evaluation of supervised learning is using metrics like accuracy, RMSE, precision, recall, while in unsupervised learning, it is using measures like cluster cohesion, sisterhood, variance explained. So now for the examples of supervised learning are spam versus non-spam email clarification, houses price prediction. For unsupervised learning, it is customer segmentation with k-means, PCA for feature reduction. Now let's look at some more explanation. In supervised learning, algorithms learn from labeled examples such as images tagged cat or dog so that they can predict labels for unseen data. In unsupervised learning, algorithms work only with their few feature vectors, aiming to group similar observation or compress information. For example, clustering customers by buying behavior when no segment label are available. Now on to the part B of question number 5, that is accuracy, precision, recall, F1 score using confusion matrix. So now let's get started. Consider a binary classification confusion matrix. True positive, correctly predicted positive cases. True negative, correctly predicted negative cases. False positive, negative cases predicted as positive. False negative, positive cases predicted as negative. So now first, accuracy. Definition. Proportion of total correct predictions is accuracy. The formula for accuracy is TP plus TN divided by TP plus TN plus FP plus FN. For precision, we have among all predicted values, how many are truly positive? Formula is TP divided by TP plus FP. Okay, so now moving forward. Third is the recall, sensitivity or true positive rate. Definition. Among all uh, among all actual positive values, how many are correctly detected? So the formula for recall is TP divided by TF plus TP plus FN. The meaning is measured ability to capture positive. High recall means few missed positive classes. For F1 score, it is the definition is harmonic mean of precision and recall. The formula is F1 is equals to 2 into precision into recall whole divided by precision plus recall, meaning balances precision and recall into small single metric, useful when classes are imbalanced and both false positive and false negatives are important. Next is question number 6. Part A says that describe how the coefficient in linear regression are estimated using either the closed form equation or gradient descendant. The part B says that explain logistic regression using the logistic function to calculate the probability of a class for a given input example. So now let's get started. The part A, estimating coefficient in linear regression. Consider multiple linear regression y is equals to xw plus epsilon, where x is the matrix of input. Each row is equals to one sample and each column is equals to one feature. W is the vector of coefficient including intercept if a column of 1s is added. Y is the vector of target values. Closed form, normal equation. First step. Define loss as a sum of squared errors. J omega is equals to 1 divided by 2m of x omega minus y to the power 2, where m is equals to number of samples. Differentiate j omega with respect to omega with set derivative to 0. The solution is omega is equals to x to the power t into x to the whole power minus 1 into x to the power t into y, provided as x to the power t into x is invertible. This directly gives the coefficient vector that minimizes squared error. It is accurate but can be expensive when number of features is very large and matrix is nearly singular. Now for the gradient descent method, start with the initial guess omega to the power 0 for example all zeros. Repeat until convergence. Here's the formula. With learning rate alpha that is greater than 0 for at least square regression gradient s. It is given that. So update rule becomes this that I have written over here. You can see that. Third step is to stop when the charge is in omega or in cos j omega becomes very small and after fixed number of iterations. Okay. The fourth step says that gradient descent is suitable for large dataset and online learning because it does not require matrix inversion, can be implemented as batch, mini batch, or stochastic gradient descendant. Okay. So now for the part B, logistic regression and probability of for a class. Logistic regression is supervised learning algorithm used for binary classifications where the target value y takes value 0 or 1 instead of modeling y directly as a linear function of inputs. It models the probability that y is equals to 1 given input vector x using logistic sigmoid function. Model and logistic functions. First step is to compute the linear combinations. Z is equals to omega to the power t x plus b, where omega is the coefficient vector and b is the bias intercept. The second step is to pass x through logistic sigmoid function that is sigma z is equals to 1 divided by 1 plus e to the power of negative of z, giving p of y is equals to 1 slash x that gives sigma times z, sigma into z, comma p y is equals to 0 slash x that gives 1 minus sigma z. The third step is the decision rule. Predict class if py is equals to 1 slash x is greater than or equals to 0.5 for another threshold, otherwise the predict class 0. Here's the example for probability calculation. Assume a simple model with two features x is equals to x1 comma x2 and learn parameters. Omega 1 is equals to 0.8, omega 2 is equals to minus 0.4 and b is equals to minus of 0.2. For a new input x1 is equals to 2, x2 is equals to 1. Compute z. Z is equals to 0.8 into 2 plus negative of 0.4 into 1 minus 0.2 that gives 1.6 minus 0.4 minus 0.2 that gives 1. Compute probability for class 1. P of y is equals to 1 slash x gives sigma of sigma into 1.0 that gives 1 upon 1 plus e to the power negative of 1 that is approximately equal to 0.73. The third step says that does the model estimates a 73% probability that the instance belonging to the class 1 with 0.5 threshold class 1 would be predicted. Now on to the question number 7. Part A says that right k-means clustering algorithm discuss how initial centroids influence the results. So part B says that right k nearest neighbors k in an algorithm using Euclidean distance. Now for the first part A, let's start. Algorithm steps for k clusters. First step, choose a number of clusters k, initialize k centroids cluster centers usually by picking k data points at random. Second, assignment step. For each data point, compute distance to every centroid, commonly Euclidean distance, and assign the point to the nearest centroid cluster. Third step, update step. After all points are assigned, recompute each centroid as the mean of all points currently in the cluster. Fourth step, repeat step. Repeat steps 2 and 3 until clear cluster assignment no longer change significantly or a maximum number iteration is reached. Fifth says that output final key clusters and their centroids. How initial centroids influence results. Different random initial centroids can lead to different final clusters because key means may converge to a local minimum of the objective function, sum of square distances. Poor initial centroids may cause empty clusters, unbalanced cluster sizes, or centroids stuck in suboptimal locations. To reduce this sensitivity, common practices are run k-means multiple times with different random starts and choose the best solution, or use smarter initialization method like k-means plus that spread the initial centroid apart. Now on to the part B, k nearest neighbors, k in an algorithm using Euclidean distance. Consider a dataset with labeled examples k to the power I, comma y to the power I, where x to the power I is a feature vector of y to the power I is a class label for regression and a numeric target. Okay, algorithm steps classification. First step, choose k the number of neighbors. An odd number like 3, 5, 7 is a common to avoid ties. The second step says that for a new unlabeled point x, compute Euclidean distance from x to every point x to the power I. D of x comma x to the power I is equals to whole root of summation j equals to I for xj minus xj to the power I to the power 2. Okay, where n is the number of features. The third step is sort all the training points by increasing distance to x and select the k closest neighbors. Fourth step says that for classification, count how many of these k neighbors belong to each class and assign to the x class with the highest count majority vote. The fifth step says that for regression, take the average or sometimes weighted average of the target values of the k neighbors as the prediction. Now we have question number 8. Part A says that compare decision tree, random forest, boosting, highlight strength and weakness for each. Part B says that explain the architecture and components of Hadoop's HDFS yarn MapReduce or describe the Spark and its advantages over MapReduce. So now let's get started. Here's the decision trees, random forest, boosting, example AdaBoost, gradient boosting from our part A. Here are the aspects from which we will be comparing them. Basic idea, decision tree. Single tree splits data using feature tests, while in random forest, many trees built on random samples and features then averaged. In boosting, sequentially builds weak learners where each correct the previous one. Bias slash variance, low bias, high variance, lower variance than a single tree, very low bias and can have high variance if overfitted. For overfitting in decision tree, prone to overfitting without pruning. For random forest, less overfitting due to its averaging of many trees. For boosting, can overfit if too many iterations or trees. Interpretability, high interpretable, easy to visualize, less interpretable, assemble of many trees for random forest, least interpretable, many weighted trees are combined in boosting. Training time, fast to train for moderate feature size for decision trees. For random forest, it is slower than one tree but parallelizable. For boosting, it is usually slower. Trees build sequentially. Performance. Decision trees are moderate accuracy. For random forests, generally higher accuracy and robust. Boosting, often highest accuracy on complex problems. Uses case for decision tree. Quick baseline model, simple rule extraction. For random forest, Tableau data where accuracy and robustness are important. For boosting, competitions, high accuracy applications like credit scoring, etc. Now for the part B, Hadoop's architecture and components, HDFS, Yarn, and MapReduce. Hadoop is a framework for distributed storage and parallel processing of big data on clusters of commonly hardware. Its core modules are HDFS for storage, Yarn for resource management, and MapReduce for processing. First, HDFS, Hadoop Distributed File System. Now let's get into it. Stores very large files by splitting them into files fixed blocks, for example 128 megabytes, and distributing these blocks across data nodes in a cluster. A name node keeps metadata, file name, block location, permissions, file data nodes store actual data blocks and periodically send heartbeats. Replication of blocks, typically 3 copies provides fault tolerance. For the second, we have Yarn, yet another resource negotiator. It acts like as a cluster resource manager and job scheduler, decoupling resources management from application logic. The resource manager assigns containers bundles of CPU and memory on nodes, managers of application and application master coordinates each application's task and monitors progress. Third is a map reduce processing model. A job is expressed as a map and reduce function. The map stage process input key value pairs and emits intermediate key value pairs. The framework groups them by key, shuffle and sort and pass them into reducers. The stage aggregates value by key to produce final outputs which are returned back to HDFS. This module automatically handles data distribution, locality and fault recovery. Spark and its advantage over MapReduce. Apache Spark is a distributed computing engine that keeps data in memory between operations using resilient distributed datasets (RDDSs) and or data frames. Key advantages over classical MapReduce are: it supports in-memory computation, so iterative algorithms and interactive queries runs much faster than disk-based MapReduce, which writes intermediate results to HDFS after each step. Provides rich high-level APIs in Scala, Python, Java, SQL, along with the libraries for machine learning, ML libraries, streaming, graph processing, graphics, and structure processing, Spark SQL. Offers flexible execution beyond map, reduce, including join filters and window operations, and complex directed acyclic graphs, workflow improving expressions and performance for many data processing tasks. Now on to the question number 9. Part A says that obtain basic logic gates from neural networks, summarize them in the table with number of neurons, activation function, and backpropagation in neural networks, if any. Part B says that computer CNNs, RNNs, GANs, and transfer learning in terms of architecture and applications. Part A. Logic gates from neural networks. A single perceptron, one neuron with suitable weights and bias can implement basic logic gates using a step activation function. The table is given as gates, Number of neurons, example weight vector, omega 1, omega 2, and bias B, activation function, comment. For AND gate, one neuron, omega is equals to omega 1 is equals to 1, omega 2 is equals to 2, B is equals to negative of 1.5, step comma binary, output 1 only when both inputs are 1. For OR gate, one neuron and the value of B is changed here, that is 0.5, negative 0.5. Output 1 when at least one input is 1. Now for NAND, one neuron single layer. Omega 1 is equals to minus 2, omega 2 is equals to minus 2, B is equals to 3. Step binary opposite of AND gate. NOR gate, one neuron single layer. Omega 1 is equals to minus 1, omega 2 is equals to minus 1, and B is equals to 0.5. Step binary opposite of OR gate. Here's the difference between CNNs, RNNs, GANs, and transfer learning, and the aspects that we will be discussing about. First, core architecture. Convolution plus pooling layers followed by dense layers. Recurrent connections, hidden state carries information in time. Two nets generator and discriminator trained in opposition. Reuse of pre-trained network for on a new related task. Data type handled. Grid-like data, images, video frames, spectrograms. Sequential data, text, speeches, time series. Any data where generator and discriminator can be defined. Images, text, audio. Any domain where similar pre-trained model exists. The main purpose is feature extraction and classification for spatial patterns, modeling temporal dependencies and sequences, generating new realistic samples resembling training in data, improving performance and reduce training time data needed. Training behavior, parallelizable, large GPUs commonly used, harder to train, vanishing exploding gradient improved by LSTM GRU units. Training is unstable, needs balance between generator and discriminator. Uh, Transfer learning usually fine tunes only last layers faster. Typical applications are image classifications, object detection, segmentation, vision task, language modeling, machine translation, speech recognition, stock prediction, image synthesis, style transfer, data augmentation, super resolution, and etc. Here's the short explanation at the end. CNNs learn local spatial features with shared weight, making them very effective and parameter effective for images and other grid data. RNNs process input sequential, maintaining a hidden state so that each output depends on previous element, useful for language and time series task. GANs pit a generator against a discriminator. The generator tries to create a fake but realistic sample, and the discriminator tries to distinguish real from fake, leading to powerful generative models. Transfer learning takes a model trained on a large generic dataset and fine-tunes some layers on a small task-specific datasets, saving computation and improving performances when labeled data is limited. So this was all for the video. I hope you like the video and explanation that I have given for the end semester paper of data science. I hope you like the video. Thank you very much for staying till the end. Thank you.